Our planet Earth, a blue oasis in the vastness of space, is in constant motion, a dynamic sphere of life and energy. We spin, we orbit, and we dance to the rhythm of cosmic forces, a ballet choreographed by gravity and time. While we experience days, nights, and seasons, there are grander cycles at play. Cycles that unfold over millennia, shaping the very fabric of our world. These cycles, known as Milankovitch cycles, hold the key to understanding Earth's past climate and perhaps offer insights into its future, revealing patterns that have guided our planet through ice ages and warm periods. Imagine Earth's journey around the Sun not as a perfect circle, but as an ellipse, stretching and retracting over vast periods, influencing the climate in subtle yet profound ways. Picture our planet tilting on its axis, like a spinning top losing its balance, a tilt that changes the distribution of sunlight across the globe. Envision this tilt itself rotating, tracing a slow circle in the cosmos, a motion known as precession, adding another layer to Earth's complex dance. These are the Milankovitch cycles, subtle but powerful variations in Earth's movement that influence the amount of solar radiation our planet receives, driving long-term climate changes that have shaped the history of life on Earth. In the early 20th century, a Serbian scientist named Milutin Milankovitch dedicated himself to unraveling the mysteries of Earth's ancient climate. He meticulously calculated the subtle variations in Earth's orbit, tilt and wobble, factors that influence the distribution of sunlight across our planet. Milankovitch proposed a revolutionary theory. These astronomical cycles drive Earth's long-term climate patterns, including the ebb and flow of ice ages. Milankovitch's theory was initially met with skepticism, as it was based on complex mathematical calculations and lacked direct observational evidence. However, his work laid the foundation for our understanding of Earth's climate system and its intricate connection to the cosmos. The first of the Milankovitch cycles is eccentricity. Earth's orbit around the Sun is not perfectly circular, but slightly elliptical. This elliptical shape, or eccentricity, changes over time, influenced by the gravitational pull of other planets in our solar system, primarily the gas giants Jupiter and Saturn. When Earth's orbit is more elliptical, our planet spends part of the year farther away from the Sun, receiving less solar radiation. Conversely, when the orbit is more circular, Earth maintains a more consistent distance from the Sun, resulting in more uniform solar heating. The cycle of eccentricity unfolds over a period of roughly 100,000 years, significantly impacting the amount of solar energy reaching different parts of Earth. The second Milankovitch cycle involves Earth's tilt, known as obliquity. This cycle is one of the key factors that influence our planet's climate over long periods. Our planet spins on its axis, which is tilted at an angle of approximately 23.5 degrees. This tilt is crucial for the distribution of sunlight across the globe. This tilt is what gives us our seasons. Without it, we wouldn't experience the variety of weather patterns and temperatures that define our year. However, this tilt is not constant. It varies over time, ranging from 22.1 to 24.5 degrees. These changes occur gradually over thousands of years. This variation in tilt is caused by the gravitational influence of the Sun and Moon on Earth's equatorial bulge. Their combined forces create a wobbling effect. When Earth's tilt is greater, the poles receive more direct sunlight during their respective summers, leading to warmer temperatures. This can significantly impact polar ice melt and global sea levels. Conversely, when the tilt is less, the poles receive less direct sunlight, resulting in cooler summers and milder winters. This can lead to more stable ice caps and less dramatic seasonal changes. The obliquity cycle has a period of about 41,000 years and plays a crucial role in regulating the severity of seasons on our planet. Understanding this cycle helps scientists predict long-term climate patterns and their potential impacts on Earth. Section 5, Procession, the wobbling world. The third Milankovitch cycle, Procession, is perhaps the most complex. Imagine Earth as a spinning top. As it spins, it also wobbles slightly on its axis. This wobble, or precession, is caused by the gravitational tug-of-war between the Sun Moon, and other celestial objects on Earth's equatorial bulge. Earth's precession cycle has a period of approximately 26,000 years. This wobble affects the timing of the seasons relative to Earth's position in its orbit. For instance, currently Earth is closest to the Sun in January during the Northern Hemisphere winter. However, due to precession, in about 13,000 years, Earth will be closest to the Sun in July during the Northern Hemisphere summer. This shift in the timing of seasons can significantly impact the severity of winters and summers. Section 6. The Symphony of Ice and Warmth. These three Milankovitch cycles, eccentricity, obliquity and procession, work in concert like instruments in an orchestra to create a complex rhythm of climate change over tens of thousands of years. Sometimes these cycles align in a way that amplifies their individual effects, leading to dramatic shifts in Earth's climate. When Earth's orbit is more elliptical, its tilt is greater, and precession favours cooler summers in the Northern Hemisphere, conditions become favourable for the expansion of ice sheets. This is because less solar radiation reaches the high latitudes during summer, allowing snow and ice to accumulate year after year. Over time, these ice sheets grow, reflecting more sunlight back into space and further amplifying the cooling effect. This positive feedback loop can plunge Earth into an ice age. Section 7. Written in the ice evidence of cycles. The evidence for Milankovitch cycles is not just theoretical, it is grounded in tangible physical data collected over decades of meticulous research. Scientists have found compelling evidence of these cycles in ice cores drilled from the polar ice caps, deep-sea sediment cores, and the fossilized remains of ancient organisms. These records are like time capsules, preserving the history of Earth's climate. These natural archives provide a glimpse into Earth's climate history, revealing a clear correlation between Milankovitch cycles and the timing of past ice ages. This correlation is evident in the data collected from various sources. For instance, ice cores from Greenland and Antarctica reveal distinct layers of ice, each layer representing a year of snowfall. These layers are like pages in a book, each telling a story of the past. By analyzing the chemical composition of these layers, scientists can determine the temperature and atmospheric composition at the time the ice was formed. This information is crucial for understanding past climate conditions. These ice cores provide a continuous record of Earth's climate dating back hundreds of thousands of years, revealing a clear pattern of glacial-interglacial cycles that align with Milankovitch's predictions. This alignment helps scientists predict future climate trends. Section 8. The Current Dilemma. Why Milankovitch cycles don't explain everything. While Milankovitch cycles provide a compelling explanation for Earth's past climate fluctuations, including the ebb and flow of ice ages, they cannot fully account for the current warming trend our planet is experiencing. The rate and magnitude of current warming far exceed what would be expected from natural climate variability alone, including Milankovitch cycles. The scientific consensus is clear. Human activities, primarily the burning of fossil fuels, are releasing massive amounts of greenhouse gases into the atmosphere. These gases trap heat, causing Earth's average temperature to rise at an unprecedented rate. This rapid warming is disrupting Earth's climate system, leading to more extreme weather events, rising sea levels, and other profound environmental changes. Section 9. The Future of Our Climate. A call for continued exploration. Understanding Milankovitch cycles is crucial for comprehending Earth's long-term climate history and predicting future climate trends. However, it is equally important to recognize the profound impact of human activities on our planet's climate system. Continued scientific research is essential for monitoring Earth's climate, understanding the complex interplay of natural and human-induced factors, and developing sustainable solutions to mitigate the impacts of climate change. Section 10. Conclusion: our pale blue dot in the grand cosmos. As we gaze upon our pale blue dot, suspended in the vastness of space, let us remember that Earth is a delicate and interconnected system. Milankovitch cycles remind us that our planet's climate is not static. It has changed dramatically in the past and will continue to change in the future. However, we are now active participants in this grand cosmic dance. By understanding the forces that shape our planet's climate, both natural and human-induced, we can make informed decisions to protect our pale blue dot for generations to come. The future of our planet lies in our hands.